Application of surface coating on abrasive grain. Now, let us look into the significance of machining with abrasive tool, where we can find one of the most important application of the abrasive grain. In this figure, what we see that on one side we have material removal rate, and on the other side it is the precision of manufacturing. Now, in this whole process, what is employed? That is the cutting tool, and this cutting tool is employed here to get a very high material removal rate, but not as high as precision which is provided by grinding. So, this is the characteristics of machining by a cutting tool. On the other hand, if we see the situation with grinding, we can see the precision is quite high, but the material removal rate is not adequate. So, that is what we see here, the machining by a cutting tool and machining by one abrasive tool, they have their own domain of application. However, this grinding can be elevated and it can attain the status of abrasive machining if we increase the material removal rate, which is comparable with that of which is provided by a cutting tool, and then this grinding becomes abrasive machining. However, to achieve this, there are at least two minimum requirements to be met. One is the abrasive material must be a high performance super abrasive, and there must be a strong bond to hold the grits. Now, if we compare a cutting tool which is used in turning, milling or drilling, and one abrasive tool which is used in abrasive machining, these abrasive grits, these are actually micro point cutting tools, and just like we use a tool holder to hold the carbide insert or a HSS bit, there must be a tool holder, and in this case this bond plays the role of the tool holder. So, it is obvious that this abrasive material which is high performance, that should be strongly held in the bond material. Now, here obviously high performance super abrasive means it must have extraordinary wear resistance, high temperature stability, chemical inertness and adequate toughness. And we know already that conventional abrasive, aluminum oxide and silicon carbide, those cannot be the best candidate for this abrasive machining purpose. So, we have to really look for some kind of grit material which is suitable for this abrasive machining. Now, here we find that this super abrasive grit material can convert this grinding or abrasive machining to super abrasive machining, and here what we get, accuracy and surface finish of super abrasive grinding plus extremely high material removal rate. So, this is one example of super abrasive machining engaging a super abrasive tool, and this is just a steel core on which a one layer of super abrasive grits are anchored or bonded, and that works at a very high speed, generating huge amount of spark, but at the same time removing large volume of material which is comparable with that of machining, but at the same time its surface quality which it is going to produce, that is as good as that of grinding. Now, what is meant by super abrasive material? As we know that conventional abrasive material which are used in traditional grinding, those are actually aluminum oxide and silicon carbide. So, aluminum oxide is used for all sort of ferrous material processing, whereas silicon carbide, that is used for processing non-ferrous material, carbide and some of say cast iron base. Now, here we can find that this diamond, that is one of the strategic material which can also be used for machining non-ferrous material, ceramic, then tungsten carbide and so on, whereas if we have our focus on cubic boron nitride, then that is earmarked, that is fixed for taking those grinding tasks as grinding of various grades of steel and which are quite hardened. So, these are the two class of materials, diamond and CBN, they are known as super abrasive, which are fit for this super abrasive machining. Here we see various types of diamond and CBN. This is one of the natural variety which is a mined one, mined diamond. This is synthetic, man-made, which is a single crystal type having a blocky shape, very strong and tough. These are used for difficult grinding task. Here we have also polycrystalline diamond, which are used for grinding delicate material, just like tungsten carbide grinding, where the material, work material is very sensitive to heat and force associated with grinding. Now, in the CBN family, what we see that basically we have two types of CBN. One is monocrystalline, that means here we have these two are monocrystalline and this is actually the microcrystalline. So, in monocrystalline we can see this is little dark in appearance, while you have the amber color. That this difference comes from the fact that this has some excess boron, that means excess boron, whereas this is having excess nitrogen, but both are of single monocrystalline type. One is blocky, very strong, but another has little friability, that means its ability to break down in a very controlled manner. Whereas this microcrystalline, it is extremely tough material, it does not have any well defined crystallographic plane, and as a result of that we do not expect, or there is no risk of any cleavage along a particular direction, and it can be used for taking any difficult grinding task. Now comes the bond for super abrasive material. As we know that if it is it has to act like a cutting tool, then this diamond or CBN, these are the cutting tool. However, the resin bond or the metal bond or even vitreous bond, they are actually the tool holder. So, very important issue here is that this material during grinding should have adequate strength, it should not crumble or crushed, it should not have any plastic deformation, have some rigidity, and at the same time it should not have any thermal damage or thermal degradation during grinding or superabrasive machining operation. So, depending upon the grinding problem, one can have a resin bond or a metal bond or even vitrified bond, and if we again look into this various types of diamond or CBN, then there is a correlation between this type of crystal and the type of bond which are best fitted for a particular grinding operation. That means, this this synthetic material diamond or CBN along with the bond material, that becomes a integral body to match a particular grinding operation, and it depends upon the work material composition, its mechanical characteristics and chemical characteristics. Now, what is mean by failure mechanism of superabrasive grinding wheel? It has been well understood that in superabrasive machining or grinding, the grit is a high performance material. So, this material has a very long service life. It is in contrast to conventional abrasive. So, what is very important in this case, that this grit material must be held with the strongest possible grip in the bond material, and this grit should not have any premature dislodgement during the course of grinding. So, what is meant by this? That this grit material with the passage of grinding can have natural wear. That means, it is the grit wear, it can be attrition or microfracturing, but this grit should not have any premature dislodgement. So, what is important here? The interface between this bond material and the grit material has to be developed with strongest possible adhesion, and that becomes the primary or the main challenge in bringing up one of the high performance tool which is supposed to work in superabrasive machining. So, here we see attritious wear, microfracture, macrofracture of the grit, these are all on the grit, but this is exactly grit pull out. That means, as a whole the grit is removed from the bond, leaving just a socket or a pocket, or it looks like a hole. So, this has to be prevented at any cost. Now, failure of the bond material, in fact, the grit and the bond, they must work like an integral body. Neither of these two should fail. So, if we consider failure of the bond, then we can see at least thermal degradation of the bond. It is particularly applicable for resin bond. If the temperature of grinding is too high, then this heat load, heat flux will be transferred by the grit material to the resin bond, and this resin bond may simply burn. Fracture of the bond, if the bond is too brittle, it can also collapse under the action of high magnitude cutting force. Yielding of the bond, if its rigidity is not too high, it can also undergo some plastic deformation. Then comes the bond erosion. Now, during the process of abrasive machining, what is going to happen? The chip material which is continuously being produced and flowing, it is flowing past the bond material which is similar to the rake surface of a cutting tool, and just like crater wear what we see on the face of the cutting tool, we can also have very similar to that which will appear as erosion on the bond. And if this erosion takes place at a faster rate, then there will not be any material support, and within a short period of time the grit will lose bond support and there could be also fallout of the grit. So, this is one very important illustration highlighting this failure mode of the wheel by this grit pull out. This can be a CBN grain or diamond grain which are bonded or anchored to the bond. However, if this bond is not adequate, which depends upon the coverage around the grit and also the nature of adhesion, what is, if it is physical adhesion, mechanical adhesion or even chemical adhesion, that will determine how strongly it is held in the bond. So, if we do not have adequate strength, adhesive strength, then it will end up, and it is going to happen within a short spell of grinding. And what we can see here, that so many number of pockets appeared, that means these grits hardly could engage themselves in effective grinding. So, what we can see, individually the grits are very strong, durable, all sort of stability, chemical, thermal, everything they possess. The bond material in its individual capacity, it has all physical, mechanical characteristics, but their interface is one of the extreme link, and that is the weakest zone, and that is why there is this large amount of pull out which has taken place. So, here we can find out some solution, some ways and means how to prevent this premature fallout of the grit. If we refer to a cutting tool where we put coating to improve its wear resistance or to reduce the friction at the chip tool or work tool interface, but in this case it is not the tool, it is the micro tool, thousands of micro tools which are very much in place in the grinding wheel and which are actively participating. Their surface is coated in order that they can have a better attachment with the bond material, and exactly for that this surface coating comes in aid of abrasive tool. However, apart from that, this coating can also protects the bond material against any thermal damage. That means this coating, that shield, that can act like a heat shield, and it is just like an encapsulation around the grit material, and it acts like a heat shield or a heat sink protecting the bond material. It can be another quality of this coating, that means if during the manufacture of this grinding wheel the bond material comes in close contact with the abrasive, during this high temperature processing of sintering or liquid phase bonding, there may be a risk that one of the constituent material of the bond may chemically or metallurgically attack the abrasive grit. So, in that case also, if a coating is given on the surface of this grit material, then a direct contact between the bond material and the grit is prevented, and that is why this attack, metallurgical or chemical, from the bond side towards the grit, that is also prevented. Here what we see, on diamond grit which are used for making one resin bonded abrasive wheel, which is exclusively used for grinding of tungsten carbide, which are used on the cutting tool. So, it is one of the very delicate and sensitive operation. That means, the force or the temperature during grinding should not be allowed to rise above a threshold value, which may otherwise cause damage to the workpiece. So, this is actually dry grinding. This is a polycrystalline diamond, which is having a good microfracturing characteristics, always keeping the grit material sharp, holding the force and temperature within a control limit. Now, this dry grinding is essential for this grinding of carbide. However, during grinding, temperature may rise, and this diamond is also sensitive to this temperature. There could be some thermal degradation of this diamond. So, in this case, this coating of copper, which is used as a heat sink, which can conduct the heat from the grinding zone, and that will be accumulated in this sheath, which is a film of copper. Now, this is a grit specifically used for dry grinding of tungsten carbide. Now, this coating of copper on this diamond grit, that can be given either by electrodeposition, that means the galvanic deposition, or also by electroless deposition. Both are possible. Now comes nickel coated diamond grit. So, these are the nickel coating on diamond grit. As we have seen that copper coated diamond grit, those are specifically meant for dry grinding. This nickel coating is given on the diamond grit. It is for wet grinding purpose. So, in this case, we can increase the material removal rate or grinding parameters. Expectedly, the temperature or force will rise, but in that case, this nickel being a poor conductor of heat, that will act like a heat shield, and it will not allow this heat flux to move towards the resin bond. Thus, the bond is protected against any thermal degradation. So, this nickel grit, nickel coated grit, here the coating is thickness of the coating or the amount of coating is assessed by the weight percent. This coating amount, it is almost about 60 to 65% by weight of that of a diamond grit. So, this is used for this wet grinding purpose, and this is used with resin bond. Now, we come to nickel coated CBN grit. one thing we have already seen, that this surface is also rough textured. That means, it is not only for protecting the grain against any heat flux or protecting the resin bond against any thermal damage, but more importantly is how to hold this grit within this resin, because the resin and the diamond, there is no chemical attachment. As a result of that, there is every chance of fallout. So, it is intentionally a rough texture is developed on this diamond surface by this particular coating process. So, when we see this is actually a CBN grit, this one too, it is coated with nickel, and here we can see the cross section of this nickel. These two pictures that show the thickness of this nickel, this is the core area, that means the original grit. Here it is a smooth coating and that is a rough textured coating, and this grits goes with a resin bond. So, here mechanical anchorage is more important, and we can have a careful look that we can see the spikes, and these spikes actually act like good mechanical anchor, and this resin bond have a firm grip on this surface, and as a result we expect longer life of this grain within the bond, and there is hardly any premature dislodgement of the grain. So, if we see the performance of this nickel coated CBN grease in resin bond, what we can see here, this black bar diagram that shows that this is the grit retained and that is the fallout. So, here we can see this fallout number is quite large, quite substantial, but when we put this coating, then we can see that retention is much better and fallout has also come down, and this difference is because of this roughness value, which is a relatively smooth coating and which is a coating with this outgrown nickel, which are acting like spike and serving like an anchor in the bonding process. So, one can immediately realize the very significance of this grain coating in reducing the premature fallout of the grit. Now comes titanium coating on superabrasive grit. So, this titanium coating is given by vacuum evaporation, ion plating or by sputtering. Now, so these are all PVD processes. For titanium, a CVD within a range of 1000-1100 is just not possible because of the chemical stability of titanium tetrachloride, which does not allow one to reduce titanium, and here these processes are well matched with this grain coating. So, this coated surface, we can have a look here. These are the titanium coating about 1 micron thick on CBN, and these are the very strong CBN grit, which is having a blocky shape. It is a monocrystalline in its structure. This is the surface morphology of that coating. Now, this coated grit can be used either in a metal bond or in a vitreous bond. Now, in metal bond, since it is ceramic and metal, there is a chemical mismatch. So, this metal bond ordinarily cannot have any chemical attachment, conventionally it can't have. However, if we provide a coating of titanium, in that case this titanium can have a chemical attachment with this CBN because of the reactivity of titanium, and at the same time this outer surface of the titanium can go well with the conventional metal bond, and there we can have a good bonding. So, it will be something like this. So, this is the CBN grain, and on that we have a titanium coating. So, this is one interface and it will be embedded in a metal matrix, and this metal matrix normally is inert towards this highly chemically stable CBN. So, inside you have CBN, this is titanium coating, and here you have the metal matrix. So, titanium is making a chemical attachment here, and then outer surface of the titanium is also making a metallurgical attachment with the metal matrix. So, this way we can have a very strong bond, but this CBN with this titanium coating can also be used in vitreous bond. Say this is for example a CBN grit over which we can put a titanium coating. This coating is essential, it is just not for enhancing the bond between the vitreous bonding agent and the grit. No, that is not the requirement. Here just outside what we have, this is CBN, this is titanium coating, and here we have vitreous bond. So, this vitreous bond contains many alkaline element and compound, which during this high processing temperature, that means high firing temperature, this vitrified bond may chemically attack CBN. This alkaline material can attack boron. So, to prevent that, a coating of titanium is well suited, and this titanium, the outer side of this titanium during this firing can become titanium oxide, and this titanium oxide can fit well with this vitreous bond chemically. So, this way this CBN grain can be also protected against any possible attack by this vitrified bond at a high firing temperature. We can also have titanium coated diamond grit. So, in this case what we see, a diamond grit, of course, these are the strongest grit what we have seen. This is the blocky, very strong, and these are meant for very challenging grinding task using diamond. So, here this is diamond. So, outside surface is coated with titanium, a coating of titanium, and just it is embedded in a metal matrix, and this metal matrix ordinarily cannot have a chemical attachment, as is the case what we have seen with CBN. So, this is the metal matrix, this is titanium film diamond. So, here we have chemical attachment because this is carbon and titanium, we expect here to form TIC, and in case of CBN what we have seen here, we expect to have TIN and TiB2. So, this chemical attachment, chemical bridge formation is quite possible because of this thermodynamic property. These are more stable than this one, this TiC is also more stable than carbon. So, this part is well accepted, but what we can see further to this, the outer surface of titanium can have good bonding with this conventional metal matrix and we get a very good bond. However, it is also observed that in certain case this metal matrix which may contain cobalt, nickel, particularly this material during this high temperature processing can also attack diamond. So, in that case, if we have a coating of nickel, that attack chances are remote and that titanium coating actually is protecting diamond. Now, in this connection it can be said further that if this is the diamond coating, then we have a primary, this is the diamond grit, we have a primary coating of titanium which has a chemical bond with diamond. However, it is seen that this titanium is actually prone to oxidation. So, if we have a titanium oxide on the outer surface, then this oxide may not facilitate bond formation with conventional metal binder. So, this surface is chemically attached. However, the whole idea is that here we have titanium carbide formation, but on this side it should be a metallic titanium, and on this metallic titanium conventional metal alloys can have chemical or metallurgical bonding. But if this titanium is exposed to atmosphere, there can be titanium oxide. Now, to prevent that, what is done? It is also a routine practice, to put a secondary coating of nickel, So, we have two coating here, the interface between this is nickel coating. So, this is the interface between titanium coating and nickel, outer surface is nickel. So, titanium is totally protected, covered, it is shielded by nickel, and this nickel is not so easily oxidized. So, conventional metal which are not very reactive, that can have very easy bond formation over this outer surface of diamond, which is now just a coating of nickel. So, this way diamond grits which are used in metal bond, where the grinding task or the abrasive machining task is one of the difficult one. So, in that case we expect to have the strongest possible bond formation between the binding agent and diamond. So, here we can see that immediate benefit out of that. We can see here that this is a diamond grit which was used in some sawing. So, it is a diamond saw, and where titanium coated grits were used, and this was without this coating. So, what we can see, cumulative radial wear, that means fallout of the material. When it is without coating you have large fallout, but when it is with coating then fallout is less or sizably less. So, the coating of titanium and a subsequent coating of nickel as and when necessary, that is found to be much more beneficial in retaining the diamond grit, and then this tools can work for a longer life and they do not suffer from premature fallout of this grit material. TIC coating on diamond grit, where the diamond grits are embedded in vitreous bond. Now, we know that TIC coating deposition by CVD, that is one of the most interesting process in the CVD technology. So, it is TiCl4 CH4 that can easily give TiC plus 4 HCl. So, this is the TiC which can be deposited on a cutting tool, but in this case it is deposited on this diamond surface, and in this case obviously first of all TiCl4 and the carbon from diamond that will participate to get a TiC sharing carbon from the core area, and followed by the actual deposition by overlay process. However, this TiC is found, TiC coating on this diamond surface is found to be quite useful, and a CVD technology very easily it can be practiced, and it can be used to have a better uniformity of the coating over the diamond surface. Of course, in this case what is necessary, it is just not a conventional reactor, but it should be a fluidized bed reactor, so that in the vertical tube reactor there will be a suspension of the grit material. So, all the reacting gases should be fed. So, it is almost like a vertical reactor, and the reacting gases will be fed from the bottom. So, here the grits will be in like, it will be like a suspended particle, and on this grit surface this reaction will take place. So, this CVD technology can be used for TiC coating on diamond. So, here we can see immediate benefit, that this one with this TiC coating, and this is without TiC coating, and this diamond was used for grinding of silicon nitride, a material like silicon nitride. And what is very interesting observation, that just by virtue of this TiC coating, the performance of this grit material is augmented significantly, and here this is the amount of wear. Without, on a uncoated grit material, this is the amount of wear. So, the benefit of this TiC coating, which can be obtained just by using the well established CVD technology for TiC, with little modification in the reactor having a fluidized bed. So, this TiC deposition on diamond grit is possible, and the benefit is immediately recognized. Now, this is another very interesting example of TiC coating application on CBN grain. Normally, what happens, CBN is extremely stable, this CBN particle, and if we put a diamond particle. So, this is CBN and this is diamond, and what is our observation, that if we have a material nickel chromium base material, and if this material comes in contact with this bond with this CBN or diamond, then this material can have very good adhesion with this diamond. It is because of the presence of chromium which makes chromium carbide, and then we have a very good bond formation. Now, this diamond, that means this carbon and chromium, that can lead to chromium carbide formation. So, free energy data actually indicates that. So, when this material becomes a liquid, then chromium segregates towards the surface and we can have a very good bonding and wetting. But this is just not possible with CBN. When we have this chromium with CBN, that means boron and nitrogen and chromium, which is actually the strategic material, but thermodynamic properties they do not suggest that chromium boride or chromium nitride are evident and they will form. That means this is more stable than these two, whereas this is more stable than carbon or diamond. So, what is done here to make it wettable? What has been done? An attempt was made, it was a success, made with success. So, in this case this TIC was deposited using the well established CVD technology, and this is the coating on this CBN grain, and this CBN grain, that is actually a monocrystalline very strong grain. It is seen that this intersection of these two crystallographic planes on this side, these are well covered, the edge is also very sharp edge, there also we have very good coverage of the coating. In the XRD diagram along with CBN, we can also recognize the peak of TIC. So, it is a titanium carbide coating phase that is that can be recognized here, and when this grit was polished and it was probed with a microprobe analyzer, and when this image of titanium was taken, it shows that entire periphery, this area. So, this is actually a polished section, and here we can see coating because of this some flaws and voids on the surface. So, this even this voids, micro voids, which are well covered by this CVD. So, this part could not be polished, remain unaffected. So, what we can see here, that the whole periphery is covered with this coating of titanium carbide, and this titanium carbide really helps in improving the wettability. As we have mentioned that when we put this CBN grain on a substrate, and here we have this liquid, this metal nickel chromium base alloy, which was melted, and after melting, when it is uncoated, it did not wet the surface. So, what actually happened, that after this melting, if these are the CBN grain, after melting, so this is a substrate on which these grits are resting. So, after melting, we have a non-wetting profile of this nickel chromium alloy. So, that means it did not wet CBN. CBN means uncoated CBN, but when it is coated with this TIC. So, now we have a TIC, these are the grains, these are the grains of CBN, and here we have a coating of TIC, and these are again resting, and here we have this binder alloy which will be melted at around 1000 degree or 1050. So, in that case what we find, that this material really have a wettability. So, this is getting wetted, and this is clearly evident in this picture. So, this is actually pulled by this coated surface, that means this TIC coating virtually pulling this alloy, thereby decreasing the interfacial surface tension. So, This is also one interesting study showing that this TIC coating, which is conventionally we use to provide a hard coating on a cutting tool or on the surface of the ball of a ball bearing, that can be well used for increasing the wettability of a metal which is otherwise is inert and non-wettable towards CBN. Just by putting this TIC coating, this alloy, this liquid becomes wettable. Also in case of diamond, what we have seen, that the vitreous bond which was otherwise not had that adhesion, and as a result of that huge amount of fallout took place. Just by applying a TIC coating, we can improve its adhesion with that vitreous bond. So, this TIC coated, so this is further we can see that when that tool was used for this grinding action, the holding was so strong that grit might have attained some fracture, but there was no fallout from this surface of this substrate. Chromium coating by CVD, that is a routine thing. Chromium coating is used mainly to graduate the property of steel to receive a coating of TIC or TIN, but here we can see that this CVD coating of chromium can be also attempted on CBN and diamond. However, what has been seen that in this case, this chromium coating, it was not, the result was not that successful, in that this coating was not appear like a continuous one. We have some island of this coating which appears to be a non-wettable, and here also the bonding is also very poor with the metal matrix. That means this coating. So, this coating of chromium on CBN, that could not be effectively given. The reason may be that this CBN is not a very good receptor surface. One reason could be that chemical stability of boron nitride is quite high, and chromium carbide and chromium nitride, this material could not be formed so easily to initiate the process of nucleation and growth of coating. However, when this was put on diamond, the result was totally different, and here even at 900 we could get a continuous coating, which is in contrast with what we can see here, and this one with 1000 we could have a crack because of the differential thermal expansion. So, if it is handled with little delicacy, then we can have a good coating of chromium over this diamond surface, and then these grains are extremely wettable. Very good wetting can be achieved with a nickel base alloy which is otherwise inert towards diamond surface. So, this chromium coating can be also used for this purpose. Coating of tungsten and molybdenum on abrasive grain by CVD can be also applied, and here of course one thing should be taken into consideration, that the reactivity of this tungsten and molybdenum towards the CBN or diamond, because unless this reactivity exists or a compound is formed, then this coating process cannot be facilitated by this CVD operation. So, in this case what we see that molybdenum and tungsten, these are the material in the group 6B, whereas titanium is a material transitional element in group 4. Obviously, stability of nitride or boride of titanium would be much higher than that of tungsten and molybdenum. However, most interesting thing with tungsten and molybdenum so far as diamond is concerned is that they are matching thermal coefficient of expansion. So, if tungsten carbide and molybdenum carbide forms during CVD as a result of interaction between the substrate and the coating, then this molybdenum and tungsten can be very good candidate for converting or modifying the surface substrate surface. Coating of diamond on CBN grain can be also given. In this case, what is going to be achieved, that diamond has good wettability towards many metal where CBN has shown its inertness. So, a coating of diamond on CBN can be a good way of enhancing the wettability of CBN surface. So, with that we come to the summary. Coating on superabrasive grit plays an important role in improving performance of the abrasive tool. Coating is used for protecting the bond material from thermal degradation during machining. It can also protect the grit material from any possible attack by the bond material at high processing temperature. The most important task performed by the coating is to improve adhesion between the bond and the grit material in order that there is no premature dislodgement of the grit from the bond. The coating can be deposited by electro or electroless deposition process. The CVD and PVD are also prospective candidates for such deposition process.